Okay, so good afternoon. So this is a work with Artem.
If you write in the corner there, it's very dark and nobody will see it. So.
This is the name of my collaborator.
Oh, okay. But afterwards, maybe you start from the screen.
Yeah, joking. With Artem Raibekas, who works in university across the bay in Rio de Janeiro, that UFI. So what I'm going to talk about the modeling of this phenomenon that you was looking at the video. So first I give some motivation, So first we'll start from a physical picture. So what do you see? So you see multi-scale phenomena, which means that there was some large-scale events, which was you put in milk, so there is a big blobs appear, and then they interact with or create smaller blobs, then they create even smaller blobs and smaller blobs, and so on. Or in the case of what's called Rayleigh-Taylor instability, if there is a heavy liquid on the top, light below, it first created small events, these events created larger events, and so on. So it can go both directions. So essentially what we have is we have a sequence of motions, and which every one has its own scale, L0, own scale in space and own scale in time. So we will call L scale, space scale, tau time scale, and we will put also U, which will be a state variable. And then there is a sequence of them. They kind of interact to each other until certain very small scale. So this will be U capital N, L capital N, tau capital N. So in the usual turbulence picture, you force the larger scale, so you put a milk. And at the very small scale, you have dissipation, so there is a viscosity which starts to act, and also there is noise, which is directly the molecular noise. So there is this picture of different scales that go from one side to another, and for you to have an idea, so usual scale, the smallest scale, usual smallest scale is millimeter. So usually this is 10 minus 3 meters. And the largest scales was, for the cup of tea, it was 10 minus 1, so 10 centimeters, and it's a T. And for other applications, like for the weather focus applications, it can be cyclone, which is sizes of kilometers, or thousand, or even 1,000 kilometers. So there is a huge difference between smaller scale and large scale, and the important part is this is the modeling of this system is scale invariant. So we have to call about scale invariance. Scale invariance means that equations of motion at every scale are the same. So if they are written in proper coordinates. So scale invariance means that equations are the same at all scales. Of course, it's here in the middle. So something becomes different at the larger scales because cup has a certain dimension, and something becomes different at very small scale. And in a sense, or in which sense the systems equations are the same at all scales? It's in the case when you number the scales in a geometric way. So we will call the scales. Well, we take the scales just as powers of 2. So largest scale will be 1, then 1/2. So this will be largest scale 1, this 1/2, 1/4, and so on. So you can think about it as a vortex size. And then there is a time scale, which is usually, you can model as a certain power of length scale. So there is a power relation. So this you can, with alpha smaller than, bigger than 0. So this you can think as turnover time. So the time at which the vortex made the full turn. And then the variable which you put at every scale.
Oh, you mean the vortices at scale Ln?
This is size.
Time tau n?
Yeah.
Okay.
Yeah.
Like
We will think of it.
is alpha less than 1 or greater than 1?
Alpha greater than 0.
No, but is it usually less than 1?
Or usually less than 1. So let's put.
So it's slower than
Yeah. Usually we will take it at 1 at the end.
square root.
Yeah.
That's it.
Well, the Kolmogorov theory for turbulence gives alpha is 2/3. And then you can think about the size of U is, you can just compute it as physicists do, you divide one by another. And this gives ln in power h, where h is 1 minus alpha, so it's smaller than 1. Okay, so this is
I can lay what?
U is a state variable. It's a variable which, dynamical variable which determines the state of the vortex, like phase, for example.
Like what?
Phase.
Phase, okay.
Angle. Yeah. Okay, so this is a kind of a general framework, and I will not be talking about really physical modeling. We will more think about the simplified models which capture the phenomenology, but essentially this is, for example, this is kind of symmetries that scale invariance that you get from ideal fluid dynamics. Okay, so then the first thing what you can infer from this is interaction time. So how much time it takes effectively for the largest scale interact to the smallest scale. So you can compute it as the time that largest scale need to interact with the next scale is usually its own typical time. So it needs tau 0 to influence the next scale. This scale needs tau 1 to influence the next scale, and so on. So interaction time would be the sum. And this you can sum up because this is a geometric sequence. You take it, so this is what? This is 1 plus 2 minus alpha plus 2 minus 2 alpha. And this is smaller than 1 over 1 minus 2 minus alpha. Does not depend on n. So what it tells you that there is a finite time at which the largest scale will influence the smallest scale, and the vice versa. Whatever you put in the smallest scale, in finite time it comes here. So that's important thing, and the kind of the lesson from this is that in order to understand what happens, it's natural to consider the limit of n goes to infinity. So this is what we call inviscid limit. So first of all, for practical applications, there is a huge difference between larger scale and small scale. And then, in principle, the interaction to the smallest scales, it all goes to constant. So it's very natural to think about this limit. So and this is what we will try to understand. So we will try to understand what is the object that we get in this limit. So first of all, the first property of the system that you can immediately see, and where one of the difficulties comes, is that in that limit, the velocity, the limiting velocity, it's what is called rough. So you see that velocity goes as, at smaller scales, the size of velocity goes as power h. So this is mean that you expect that it's h Holder continuous, so it's not Lipschitz. And so that you expect h Holder continuity, which means non-Lipschitz.
Can you explain how you got that relation UN is ln over Tn?
Say it again?
Well, that's just the definition.
No, this is just definition. This is just definition. So it means that we will not have no uniqueness. No uniqueness. So we will expect non-uniqueness. We will see directly that it really happens. So if you expect non-uniqueness of the solution in this limit, then it immediately signals that there will be trouble. Okay, so now let's see the model. So let's try to create a model which will be simple, solvable, and contain all these properties. So the model that we suggest is that today I will show you about a very specific model. So first of all, we will use this dynamical system thinking. So dynamical system thinking suggests that it's much more useful to work with discrete time than with continuous time. So discrete time. But we cannot use just usual discrete time because the time that each vortex moves at different scale are different. So what? Clocks are different. So we will use time which are integers of turnover time. So we'll use different clocks at every scale. So that means that our space with time here in one direction, and here we will put scales L0, L1, L2, and so on. So at the largest scale, our time step will be 1. At the next scale, so also what we will do is we'll take alpha equals 0, h equals, no, I equal 1, h equals 0. So that power is, there's no power. Take time step the same as the length. So the next, the time step 1 for the largest vortex, the next vortex will go at 1/2. The next vortex turns at 1/4, and so on. So that's our space-time. So we will work. So this scale invariance is just directly suggests that we have a fractal space-time. So at every node of this lattice, we have a variable, which is a state of our vortex at this scale and that time. So that is the space-time. So the next step is what we will do. We will write equation of motion.
Didn't we make that 1, the u's? You said that h was 0, so the u answer all 1.
It's not that.
We do no way around. No, h is 1, No, H0, yeah, H01.
It's not actually that definition, right? You're not taking it.
Say again? What did I do?
See, it says UN is comparable to LN over.
H1, yeah, it's H is
It's H is, I think H is zero.
H is 0, alpha,
I don't understand what this UN of T is. I don't understand what's UN of T.
UN of T, it's a value, is the angle of the nth vortex at time t.
But it's always 1.
No, it's order 1. It will move. It will change. It's just order 1.
When you look at your clock, the only time you're allowed to look at the picture.
Oh, that's now what we'll do. That's not now what we'll do. So then now we have to make a law how they change, and so somehow just tomorrow I'm giving a talk on the dynamical system seminar, and we will consider general form of these models. So today let's just consider one specific model which is completely solvable. So what we do is, so the equations of motion should be exactly the same at all scales. So in other words, at every cell the law should be just the same. And what we will do is we will consider UN. So you see, UN is just like think of UN as just angle corresponding to the vortex. So we will consider UN to be a point on a torus. So we assume that a state of each vortex is fully described by 2 angles.
I don't understand that symbol.
T2.
Torus.
Torus.
It's a S1 cross S1.
That's good.
Yeah, but why is that the answer?
No, it's not.
Oh, it's in the torus. But why are there 2?
Just I want to be 2.
Got it.
Okay. And so the next, what I will do is I will put a simple law. So I want. So if we have a state of the vortex at one time, then after it moves to another time, we will put some operator which changes it over 1 to an over. And also it should interact between the neighbors. And we will only make interaction with a smaller scale, also for simplicity. And we put also operator A here. So the law is like this. UN at next time equal operator multiplied by UN at previous time plus the same operator UN plus 1 previous time. So that's equation of motion. And this is equation of motion is so there is no physical reason for this equation of motion, but the physical reason is that it satisfies all the properties I just told. So what it gives you that.
Right, UN plus 1 on the left. I'm a little worried.
Oh, no, yeah. So you see what happens. So having this value and this value, you know what is here.
The N is going down.
N is going down. So if you want to know what is at certain moment, you should just know what was at the point previous to another time and at just moment.
Just curious.
Mm-hmm. And it's exactly the same at every cell. And then we take A to be Arnold cat map. So that's Arnold.
And also. Oh, that's Arnold's cat. Okay.
It's Arnold's cat. So that's essentially the reason why I used 2 angles is because I wanted to map. Well, this is a linear hyperbolic and it's area preserving. So just for having, I don't need really all these properties, but kind of. Okay. So that's it. So now that's a model we will solve. So now we just want to make all this program of studying these dynamics on that example. So this is kind of very, very simplified example of what you would think about Navier-Stokes equation for turbulence. So the Navier-Stokes equations are very complicated, and this is a kind of captures many. We'll see that it captures many non-trivial issues. So first is let us study that issue. That what
we cannot obtain it as some approximation to Navier-Stokes, so it is just.
You see, it can be obtained as a some approximation of Navier-Stokes if this belongs to some general space, which we in that case just took as torus. And if you substitute this law by something more complex. So in the sense that giving this value is a function of something before. So in that sense, it is conceptually some approximation. But if
such will have these properties.
all have all these properties. So if I put it more complicated, so for now the advantage is that we will be able to solve, and we will see what properties this model has, and we will then see how these properties extend to more general models. So the first is initial value. So first is let's consider ideal system, which means that it never ends. Right? So this fractal goes to infinity. And then consider the initial value property. It means that you at initial time you give certain initial condition. We have initial condition, and I want to find a solution. Solution means that it satisfies the initial condition and it satisfies this equation at every node. So that can be solved directly on the blackboard. I probably need. I will just graphically show you the solution. So these are initial conditions. So these nodes we know. Then automatically
Like time goes to the right.
time goes to the right. Yeah, this is time.
And what did you say about
This is time 0.
what did you say about the last three dot circles you drew? What did you say?
What do you mean?
Did you say something about those circles?
No, this is initial condition.
Huh?
This is initial condition.
Oh.
This time 0, so we give u0 at time 0, u1 at time 0, 2 at time 0, so on. So we give an initial condition. I want to solve the problem.
0 or 1.
Well, un0 is given value for all n. So n is n.
This dot, 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 0, 1, dot, dot.
Yeah, this n.
Okay. Dot, dot, dot.
Dot, 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 yeah.
Yeah, okay.
Sorry. So that's about not visible in the corner, right? So the first step is simple. So we have this law. It means that having these 2 points, we know what is here. Having these 2 points, we know what is here. Having these 2 points, we know what is here, right? Because
You're supposed to picture the initial condition as a bunch of vortices going down.
initial condition is that we have all vortices of all sizes available, and this defines state of each vortex, phase of each vortex. Yeah. So let's think in this. So immediately we know what happens with first vortex after 1 over time, because this is just given by the previous values, this is given by the previous values. So after first over time, everything is, sorry. Everything is known. So we will call it, I call it for some reason G. So this is points where we already know the solution uniquely. And then it becomes harder. So what turns out that you can put arbitrary value here. You can put arbitrary value here. And arbitrary value at every, you see, point which is in the middle of the upper cell. So I call it R. So imagine that you put arbitrary value everywhere, at every cell of this type, and then what you see is that this equation can be solved with respect to any of the variables if the two other are given, because A is invertible. So you see that in this triangular, these two values are known. That means that you know what is here. In this triangular, the two values are known, you know what is here, and so on. So what I actually proved is that this will be B. So let's call it the theorem. So given initial condition, all solutions have the form. So this should satisfy three properties. So set any values at these spots, the squares. Define, and then all other values at these spots are given by initial conditions uniquely, and values at the blue spots are given by initial conditions and chosen values which was chosen before. So what I want to say is that we can find all solutions, and there are a huge amount of them.
So the initial condition doesn't define.
The initial conditions do not define uniquely the solution, which we kind of anticipated already from this Holder continuity. That is kind of compared ODE with yeah. But here, even on with a discrete time model, we just see directly. So given initial conditions do not define solution uniquely. And this model is simple enough that we can find all the solutions.
A lot more orange going down.
It's actually it's more or less every second. Yeah, every t has arbitrary value. So there's a huge non-uniqueness.
Dyadic like that, and then stuff can emerge at much lower scales that you can't control in the upper scales.
Yeah, exactly. So we know all this. So that's already first property. So how are you?
Is there interpretation of this with hyperbolic geometry? Because this picture is exactly like hyperbolic geometry of the disk.
I would like to learn about this more. So my motivation was more in this non-uniqueness is a rather active topic of research for the Euler-Navier-Stokes equations nowadays. For example, in the last decayed using this, I don't know if you've heard these techniques of convex integration. They succeeded to prove that for Euler equation, given the initial conditions, there is infinitely many solutions. So this is kind of a weak solution. So this is actually a weak solution in a sense for. Okay, so then what we do next? So if we cannot solve it, so let's do what physicists do in these situations, is we take a regularized system. I erased it, but if you remember that there was some capital N, which was the smallest vortex. And usually in liquids, what happens is that the smaller than certain scale, all motion is killed by viscosity. So nothing happens below the smallest scale. So what we will do is we will take some N, the smallest, which labels the smallest vortex, and set UNT to be 0 for all N bigger than N.
Quick question. Does anything interesting happen when you take those filled in white values that are determined by the initial conditions and then just make
No, you cannot continue.
Like define all the yellow ones to be those determined white values, because you can just move it over and define all of those yellow values to be those determined.
Yeah, you can do. You can have even other interesting situations with this. For example, you can take 0 initial condition, absolutely 0, and then you have just 0 until a certain moment. Then some behavior starts, and then it again becomes 0 everywhere. So this is another thing which was discovered in Euler equation for weak solution, which they call wild solution. So the weak solution of the equation, Euler equation of fluid dynamics, where nothing happens at a certain moment, and then something starts to move, and then again nothing happens. So that's certainly unphysical, but so you can play with this. This is good. But what we will do is, what we do now is we say that there is certain level and capital, and all below we just force to be 0. And at the moment you put 0 here, solution is unique automatically. Yeah, because you take any spot, it should be given by these 2 values. Every of the values given by previous. At making like this, you either go to the vertical line in the initial condition, or you go to that line. So solution from now on is unique. So there is unique solution for any initial condition, but it depends on this capital N. So for every N capital, we get the solution. Okay, and then there is a sequential. It's called sequential compactness property, which tells that you can take a sequence of these capital N's, which goes to infinity, such that the solution converges at all scales in time pointwise. So you can choose, you can take one cutoff and take a solution. Then you can take a small cutoff, small, and you can choose them in such a way that it converges. And it converges to solution, converges to a solution of the ideal system.
These are the strong solutions.
No, this is still weak solution. It's still weak solution. It converges to a weak solution of the full system. This is a strong kind of strong solution.
You choose another sequence, it could converge.
That's exactly the point. You can prove it here.
So what's the point?
The point is, so you can choose, so first is a positive knowledge, is that if you choose it, you can take cutoffs lower, lower, and lower, so that everything converges, and what it converges will be a solution, one of these solutions. So in that way, you select solution in kind of physically reasonable way. But the question whether this is unique, because this property does not guarantee that taking different convergent subsequence will give exactly the same solution. You see, depends on this sequence.
The sequence bands.
Yeah.
Unlimited exist, or is it just
You guarantee that there are sequences which converge, for which this limit exists everywhere. So you can take sequence of cutoffs, so that at every point the regularized solution converge, and the object which you get in the limit solves the problem.
You're saying that there's like a subset of solutions that are zero below a certain level. If you look at the set of all such things, that's sequentially compact.
Yeah.
That's the statement.
Is it clear? No?
It doesn't mean anything. Like you can take another subsequence, it can converge to something else. It just means you can choose some convergent subsequence.
You see, so you can physically it means that I want to kill the motion at smaller and smaller and smaller scales, and in this limit I recover solution of the ideal system.
Will you obtain all the solutions?
That's not yet. So first theorem is I'll call it theorem is proposition. Okay. So
That would mean that the stable solution
A priori bounds. Can you call this kind of property a priori bounds? Some kind of a priori bounds, so in PTE would correspond to
well, this is I don't know exactly what you mean, but this is analogous to what also known for many situations in PDEs. So, but essentially by the same reasons. So there is certain compactness property that tells you that for example, that you take in Navier-Stokes, you take viscosity smaller and smaller, smaller. You can choose values such that you converge. But the theorem tells you that
when you say converge, you mean some subsequence
converges. This is a subsequence convergence. So there is a subsequence which converges.
No, subsequence of the i's or the ni's?
Original you have. Our original sequence is 1, 2, 3, 4, 5, 6, and so on, and then subsequence of it converges. So for any sequence, there is this convergent subsequence.
Meaning it's pointwise.
For any sequence of the cutoffs, there is this always convergent subsequence.
But it's a
what?
Of the solution.
But it's a
Any sequence of cutoffs is pretty compact.
Yeah.
But it's a pointwise convergence also.
It's pointwise convergence.
Look at the logic of the sentence. I mean, there's two parameters, so it's independent of the ni's, the statement. The situation looks the same for any sequence of cutoffs. The logical situation the same for any sequence.
Yeah. Okay. So the good part of this model is what you can consider the initial condition, which is just same number, same number.
This precompactness is immediate because it is pointwise conversion, so it is just that each UN belongs to the solution.
Well, the pointwise convergence it follows from
Because UN belongs to the circle, so you have compactness.
Yeah. For each.
It's immediate.
It's kind of okay. So consider initial condition where you put the same state at every variable. So what you can prove that for almost every A, there are infinitely many solutions that are obtained as a limit, as this limit. So what I'm telling that for this system, you can just prove that whenever you put the same initial condition at each node, you can find infinitely many solutions by choosing different sequences. I don't have time to show the proof. What you can do that you
I thought you said by choosing different.
by choosing different subsequences. You can choose different subsequences and obtain different solutions. And you can prove that infinitely many solutions can be obtained.
I'm totally lost.
So,
What we're taking subsequent, I mean,
the idea is that I want to choose the good solution. We have infinitely many. So I say that okay, I want to make it in a regularized way. So I cut it here, get some solution. Cut it lower, get some solution. And what first I said that I can make the cutoff lower, lower, and lower, so that everything converges. So the next statement tells you that this way does not select unique solutions. You have guaranteed that you will have infinitely many still. So it means that the strategy doesn't work. Let's write it down.
So your hypothesis is non-unique.
Yeah, you're still non-unique.
Is there a solution that cannot be obtained?
Probably, yeah. Well, this I don't know. I just can prove that this doesn't work. So then, I think I will be able. So then, the next step, what we do, let's remember that there is noise at small scale.
so we're still using the same A, right?
I think that's the way.
Same A, that way.
Same system.
The cat.
Same system, the cat, the same system.
But then there is a subset of the finitely terminated, so that is compacted. So there must be some lots of solutions you cannot get.
But this kind of theorem never tells you that it's unique or not. So here you can prove it's strongly non-unique. So even if in this strategy you don't select anything. So now we remember that physically we have always noise. So at small scale there is a kind of small fluctuations, molecular noise. And let's put this noise into the system. So what we will do is before we put in zeros, we put at n plus first scale, we put random numbers here. Like noise. We put random numbers and then zeros. And then we take the limit. So noise means, so we will take regularization where un of t is IID random when n is just below cutoff. It's IID random and absolutely continuous. I'm just not writing it. And then it will be 0 when n is so absolutely continuous. And when is bigger than n plus 1, it is 0. So I just added random numbers just before I killed everything by noise. Or just before I kill it in motion, I put random numbers. So far, I'm not giving which ones. I only need that it's absolutely continuous. So what we have in this case?
This time you're not. In the previous one, you were just giving initial position.
Yeah. So now I'm giving some.
You're giving what happens in all of history.
But this is, I already did this. Whenever I make a cutoff, I'm giving 0 at all the history. So now instead of giving 0, I'm adding the whole history of random numbers.
Like you're trying to make it 0, but you fail slightly.
Fail slightly, yeah. So then there is so for any n, I can finish soon. Huh?
Can you state a theorem?
No, it's let me see for. No, not yet theorem.
Okay.
Not yet theorem. So for any n, there is a unique probabilistic solution. Which is a measure. So why it exists? Because we put these values which are random numbers. So for each realization we have a unique solution. So automatically we get a measure on a space of solutions. So there is a certain measure. The measure on a space of fields on this lattice. And we now will take a limit n goes to infinity for that measure. I will write theorem, but we consider first write the limits. We consider
Equation's not satisfied anymore.
equations are satisfied for each realization. Whenever for each realization of the noise, equation satisfies every.
Oh, you put those along the T dots, along the T's, like the orange.
I put noise here, and whenever you put noise here, here is unique, defined uniquely by these values and these values. So we consider the limit n goes to infinity of that measure, and so this will be weak. This will be weak in the product topology limit, and also it's not subsequence. So kind of honest limit. So the theorem tells that for any initial condition, there exists a limit mu. So it converges to the limit. And first, the properties. So mu does not depend on regularization. So this doesn't care what is the distribution of this random number. Well, the first property is implied by others, but it's a good property. So mu is supported on a set of
These random numbers are independent? Or?
independent.
They're also identically distributed. So you can
Actually, it doesn't matter what you put here. It's enough just to put just one random number here. It will work. Yeah, but let's see this identically IID absolutely continuous. What's important? So mu is supported on a set of all solutions. So whatever realization will be a solution, which is kind of natural. And the third is that mu, actually the third implies all the previous. So mu is a uniform measure on this orange point. So essentially, the limit of the sequence will be always a measure, which is just give a uniform distribution of the orange point, and all the rest is uniquely defined. So in other words, if I put noise, I will randomly take any solutions that can exist. So it's kind of the property that we have is anti-selection. So it turned out that if you put noise in the system and take a limit of n goes to the infinity, you don't need any subsequence choice, and it doesn't matter which noise you put. You get always the same solution, which is arbitrary choice of any of the solutions that we had.
These are probability measures, right?
This is a probability measure, yeah.
How do you get a uniform measure on this infinite set?
Well, that's the idea of the proof is that since it's a linear map, you can actually compute, at least you can write a formula how this value depends on what is here and what is here. And then what you prove is that, and this will be certain polynomial of the Arnold-Cat map. And then you prove that as n goes to infinity, the powers of polynomials that enter to every point become infinitely different. And then you can really prove, and then what you prove is you can prove that for any finite number of nodes, you get uniform.
Wait, but I still don't understand.
I agree that it's not trivial property. So
No, it doesn't make sense, is what I'm saying.
Oh, really?
A sort of an subset that maybe
Is it not?
No, but it's a uniform measure. So let's say, it assigns to one of the orange pieces the number 0.28. Then that means that the sum of 0.28 from 1 to infinity is 1. It's a probability measure, you said, right?
So what I'm, you see,
He knows that, so we're not understanding.
no.
I don't understand either. The sentence is permutation, illogical, but let's understand what he means.
Well, what I'm telling that you can define for each node, for each orange node, you define the uniform measure on the torus. Okay. Then for the probability measure that controls all orange points is a product. Product. So it gives you arbitrary choice for the product measure. And then for the rest, you don't need to define because the rest is uniquely defined. So it's Dirac delta. It's better, no? So what you can prove that whatever noise you put, the limit will be that. Exactly the same.
Could you modify just to make sure that the limit depends on the noise that you put in?
I'm only the limit is on at which scale I put the noise, and then I take it lower, and not in a subsequence. It's true.
If you change the type of the noise, would you change the?
If you put the same noise, whatever noise you put, it will be the same limit. I don't change it with n.
Are you saying change the distribution?
Yeah, if you change the distribution. Does the limit change?
Change the,
You're saying instead of
no, this is for any distribution of noise.
So mu does not depend on the polarization.
Yeah.
It means that it doesn't depend on this distribution of this random numbers.
He even said that it doesn't even depend on anything except the first entry.
Yeah. Okay, so I think I have to finish. So I probably give you some further ideas, just formulation of the further ideas. So essentially, why this happens? So why, if you put noise, somehow everything starts to converge? By the way, this convergence is extremely fast. So it's convergence in n is double exponential. So essentially, it's not even. I mean that if numerically, if you put 10 minus 50 noise at the level n equal, like I remember 10, here you will everything will be perfectly convergent. To probably forget it. Okay, so what the idea? I'm going to talk tomorrow. So that it turns out that if you define an evolution map, which is psi n, which maps initial condition to un at time 1. So let's define evolution maps that maps initial condition to the to what happened at time 1. So what you can prove?
Capital N on the left and no capital N on the right.
See here?
Is that capital N?
Capital N is...
no, this is capital N is where we cut. And this is a vector of all.
Oh, okay.
That's the random situation or...
Oh. So if it's deterministic, it's a map. If a random, it's probability kernel. Right. So then what you can prove is that Cn plus 1 can be written as, so what is Cn plus 1? Cn plus 1 is an operator which acts on Cn. An operator you can find. Do I have to finish?
Your renormalization.
Yeah, do I have to finish? 5 minutes? No, it's okay. So I'll just can show you how to derive it. So this is our lattice. So our map maps initial condition to condition at time 1. So now let's find what happens if we regularize at one step below. What we use is we use the fact that the lattice is fully self-similar. So what you have in this block is just the same as what we had in that block. Only this block is cut at one scale smaller. Right? So this block had cutoff at n plus 1, and this block has exactly the same equation if you forget everything around, but it will become that the evolution from here, no. Evolution from here to here is taken by Cn map. And evolution from there to there, it's another Cn map. And then there is an extra block, which is above. So what is this? So this is you have to cut the first element. Just take this vector, which is actually shift. So sigma 1 is the operation which removes the first element. Then you move by Pn twice. And then you should add 0 element above. So it's inverse shift. And then you have to add just two interactions which is on this block which you didn't put. Last side. So what you see is that increasing n is just applying certain operator to the evolution map. And
What's that term you added? What is plus something?
plus xi we need to add because this doesn't take care of this. The last term doesn't take care of that. There is also some dynamic on the upper cell. And first of all, this term is quite, I think many are very familiar with, because this is a Feigenbaum type term. Feigenbaum. Because it's scaling, shift is a scaling, because change of shift in scales, it's multiplying all scales by 2 or dividing by 2. Scaling, backward scaling, and twice operation.
But you first apply sigma minus.
But in opposite direction, yeah. So instead, not if you first. So in Feigenbaum it will be minus plus. And then there is one more term which makes the renormalization group is intrinsic.
The way you said it, composition is the opposite. Usually, when we do composition, like it's you go from the right to the left.
Well, I said it. What I meant is correct, but what I said is wrong. So this is plus. So you moved, then you do this and do this. Okay, yeah. That's my bad. So essentially, what this tells that the implicit limit is a limit that you obtain from. So essentially, what you
F of x should have been written x f. Take an x, apply f.
It depends if you're
We can
more
just read
speaking
from left to
Hebrew or
right.
English.
I've suffered for years because of that.
If you grew up in Israel, it would be easier. We write the other way.
So what I did wrong?
No, it's just notation, F of x.
So essentially, ideal model give us operator, regularization give us initial map. Yeah, because the regularization gives us a map which was just cut right here, and the RG dynamics gives a limiting behavior. So apparently what we have here is that the RG dynamics for this R operator is chaotic, and the limit is this measure.
And the limit
Is that measure that kernel that I showed. So just very last conclusion is.
This is part of the proof. This is related to the proof.
No, this is interpretation of the proof.
Summary?
This is a summary of the result, because proof is just brute force. But this idea, it's already not only works for this model, but for the whole class of models. So this idea that I'll try to explain tomorrow, that this idea already works for much larger class of models, which much more sophisticated behaviors. And
What's the statement that involves normalization?
so essentially, this final statement is the following. So if for final statement that if RG dynamics converges to a. So if has a limit. Then if the limit is a fixed point, if the limit of the, so I say it in words. So if the limit is a fixed point, that means that we select just single solution, whatever regularization you have. So single solution will be selected. But if the limit is a measure, then the dynamics that we select is a Markov process.
Markov process.
Yeah. So final idea is that these RG dynamics, which is now, instead of time, you use cutoff time. If this dynamics is chaotic and you have a chaotic limit, this chaotic limit defines, for original system, it defines a Markov process as a solution. So that's essentially the idea.